Okay, so we're kind of making this connection between, our I think I've mentioned in here before that we want to think about our computer as kind of a collection of resources, and everything we do is about sharing those resources. And so now we're looking at directly talking to our CPU, even though that's not necessarily what we really want to do, but at the under the hood, we know that's what's happening, right? And then we know that our CPU has to work hand in hand with one of our other resources, like our system memory, for storing larger chunks of data that doesn't necessarily need to be as fast, but is, it's of scale. All right. So that's where we store base addresses, and we're looking at C, and we've seen the same kind of pattern in C for doing this. Okay, so this is just more memory stuff. Pretty similar thing here. We're going to store at our memory address. So this is kind of adding some, connecting some of the dots for our load and store stuff. So if we wrote the high level code, we had an array named A at bucket 12 is going to equal H plus A at bucket 8. So they've said that H is this x21. So this is this 35. All right, that's what my variable H is. So they've moved that into bucket 21, or my register 21. So they want us to overwrite, or potentially not overwrite, but write into memory at base address A plus offset 12. All right. They want us to write into memory at that location whatever H is plus the value that currently lives at address 8. That makes sense? Okay, now notice that they're talking about these guys as being words now, so those are 32-bit jumps. So that means the first value, so A at bucket 0 will be, so 32 bits is 4 bytes, right? That will live here, 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 so those 4. 1, 2, 3, 4. That's the very first bucket of our array will live there. Then, bucket 32, so this is 1, 2, 3, 4. They're having you go to bucket 8, so they're doing, so these words are smaller. So bucket 8 is, that's 64, so that is, all right, so these are 1 byte buckets, the way they're dealing this example. So this is bucket 0. This is bucket 1 at memory address 5008. This is bucket 2 at 5016. Bucket 3, bucket 4, bucket 5, bucket 6, bucket 7, bucket 8 at 5064. Okay, so they're saying we're going to load into X9. So we're going to load into a register the value that lives at base address 5000 plus 64. So we're going to load this 25 into X9. So it was 25 initially. All right. Then we're going to add. So this is kind of showing if we wrote the high level code like this. This might be the Java code or the C++ code or something like that. If we wrote this, that one line is going to turn into these 3 lines once we compile it. So when we talk about a compiler translates from a high level language into a low level language. Okay. We'll throw that in the slides and remember that. So we have this tool that's a compiler. Translates from a high level language to a low level language. Okay, and why do we have that? Why do we like that? It's because humans like power tools. Computers like binary. So we need something in the middle. So we go from our power tool language, which is a high level language like C or C++, use a compiler to get it into a low level language. Okay? And then we translate, we use an assembler to get it from that low level language into the equivalent zeros and ones, which we'll look at. That's the next step. Okay? So what we're looking at here is if we were the compiler, if we had to write the code that took a line of syntax in C, like this, and converted it into the equivalent, the functionally equivalent low-level code, in this case, our leg, whatever, ARM assembly code. Okay. Now, keep in mind, there might be more than one way to pull this off. So the best compilers will give you a more optimal solution. But as the human compiler goes, from our perspective, we want to think about it from, we're going to be pretty happy with it being functionally equivalent. Okay? So the very first thing we're going to do here, so they're assuming that these values have already been loaded in. So there's actually some missing lines here because they're just showing you how do you map this single high-level instruction into the equivalent low-level instructions. All right? So the very first thing I'm going to do is I'm going to load into X9 the value that lives here. All right? So we went ahead and grabbed bucket 8 of my array, which lives at an offset of 64 bits from the base address. So there's my 25, so I loaded that into X9. Okay, that's step 1. Step 2 is I'm going to take whatever's in X21, which was previously loaded, so earlier high-level commands, and I'm going to take what's currently in X9. I'm going to add those guys together, storing the result back in X9. So that'll give me a 60 in X9, overwriting the 25. All right. Finally, I'm going to store from X9. So I'm using X9 as my source. So store my 60 into a place in memory that's going to be equivalent to 12, bucket 12 of this guy. All right, so that should be 12 times 8, which is 96. Is that right? 12 times 8, 96, yep. So they're saying that each bucket is 8 bits. So we're going to go to memory address for bucket 12. I'm going to go to memory address, base address plus 96, which gets me down here. This is the equivalent of bucket 12. And I'm going to store the current value of X9 at that memory location. So keep in mind that this line moves something from system memory into register space. This line takes something from register space and puts it back into system memory. These two lines here are the communication between your CPU and system memory. Go ahead.
Would this be like your RAM, or would this be like your cache?
RAM, yeah. Definitely RAM.
Okay.
Yeah, cache is going to be more of the CPU architecture, so you're going to have specific instructions for working directly with cache.
Okay.
Yeah, cache is going to be more like a fat register than system memory. System memory you want to think about as being a fast hard drive from a CPU's perspective. So you almost want to just drop all the levels down one. So when we're dealing with a computer, we think of memory as being fast, and we think of our hard drive as being slow. If we turn ourselves into the CPU, we're going to think of our registers as being fast, as well as cache being pretty fast, and our system memory as being the hard drive, right? And the hard drive is ridiculously slow. In fact, the CPU is not even going to deal with the hard drive. The CPU is relying on the operating system to do any magic when you're writing to the file system or something like that. It's just too slow, too slow. All right, so does this make sense? So this line right here is us bringing something from memory into register space. This line right here, so this is load. So load from memory into register space, store from register into memory space. Okay? So we're seeing that transition between those two resources. And then this is our little mathy stuff in the middle. CPUs are really good at this. So this instruction would happen real quick. Fast memory, do a quick add, which is a magic trick that's written in hardware. Fast. Okay, so that's kind of what we were just doing here. So it's another interactive thing. It's just that loading and storing stuff. And this is just talking different operating systems, what the size of their integers are, and long integers. And well, in C, we have something called a long int, which gives you extra space. And then what's the size of a pointer? So they're saying modernly our operating systems are 64-bit operating systems, so address space is 64 bits, so that's why our pointer size is 64 bits. Okay, so now, before we jump into this gets into our binary stuff. So we've already done binary conversion and that kind of stuff, so we're all pretty comfortable with taking a binary number and turning it into decimal or octal or something like that. We can go from decimal and octal back into binary. So that's comfortable stuff for us. We might not love it, but we can do it. Okay. So now, let's think about binary math for a few minutes. So let's say I have the number 1011. Let's just do it with nibbles. Have I used that word before, nibble, in here? So 4 bits is a nibble. Okay. So we're going to say 1011, and we're going to add 1001 to that. So we want to add these two values together using binary math. All right. So as a starting point here, backspace. Let's say I have the number 21. And I want to add to that the number 48. So let's deal with decimal numbers first. All right, so I'm going to add these guys together. So we're doing addition. All right, so this becomes kind of a funny thing because a lot of us we learned this stuff back in second grade, third grade, and we don't really do it by hand anymore, right? We use a calculator or something like that, so we've almost kind of forgotten some of the moves. And it's going to be important that we remember that stuff so we can do the math the other way. Okay, so if I want to add these guys together, I want to take the 8 plus the 1, and that's going to give me a 9, right? So I'll record the 9 down here. All right, then we go over here. We have the 4 plus the 2. That's going to give me a 6. So there's our 69 with those two guys added together, right? Now, what if that was a 5? 8 plus 5 is a 13. So what do I write down here if it's a 13? I write the 3, and then I'm going to carry a 1, right? So I'm carrying a value here. Now I do 4 plus 2 plus 1, which gives me my 7. That's my 73. Make sense? Okay, now let's make it a little bit worse. What if that guy was a 9? So now I have a 9 plus 4, which is a 13, plus 1, which is a 14. So now I'm going to put a 4. And I'm going to carry. Now, here, I'll just steal this carry bit. Carry a 1, and then that just drops down to 143. Right? So now we have to think about what happens with carries. So let's, when I was giving you my answer here, and I came out with 143, that just seemed like it was so obvious, right? Because when we're speaking out an answer, when I'm saying 143, or if I'm writing it on a piece of paper, I'm only constrained by how big my piece of paper is or how loud I can speak to the room. I don't have to worry about whether or not I have room to store this 1. Just dropped it down. 143, there's my answer. Now, if you're dealing with a 8-bit register, and all of a sudden you have a carry bit on bit 8, you have nowhere to put that carry bit. You're out of space. Is it like when you fill up the bathtub but don't turn the water off? Okay, eventually the bathtub's filled. And then there's water on the floor. Make sense? You run out of space, it's got to go somewhere. All right, so we're going to talk about how to handle some of that stuff as well. So let's go ahead and give myself my representation here. So this is 1, 0. 1, 1. And then I'll steal this guy. This is 1, 0, 0, 1. All right, we're adding these guys together. So now we're doing this in binary math. Our only legal bits are 0 and 1. So 1 plus 1 is a 0 with a 1 carry. 1 plus 0 plus 1 is a 0 with a 1 carry. 0 plus 0 plus 1 is a 1. 1 plus 1 is a 0 with a 1 carry. And we can drop that down, and we know that that's going to be the correct answer. But then the question for us comes down to, depending on if we're working in a register, do I have room for that? Or is the bathtub too filled? Make sense? All right, so that's where we have to start looking at carry flags and stuff like that. Not that important for us at this exact moment, but certainly important when we write this stuff. Okay, so binary math, pretty much the same as decimal math. Do you suspect that hexadecimal math is also the same? It's the same. Just when you carry, you're carrying off of base 16 instead of base 10 versus base 2. So your carry bits mean something a little different. It's just different magnitude values. Okay, so now let's, here, I'm just going to create a new slide here. We'll write this. So at this point, we've been working with unsigned numbers, so only positive values. All right. So the number 3 in binary is a 0, 1 in the 2's place, 1 in the 1's place. So if we write it as a nibble, it looks like that. All right. What if we want to represent the number -3? So we got to go back. And we're going to talk in a few minutes how it's actually done today. We have to go back to the early days of computing and ask ourselves, okay, how could I represent negative numbers? All right. So one approach to this is something called sign and magnitude. So this might be kind of the simplest approach. You might just say, look, in our little world here, we're dealing with 4-bit numbers, right? Nibble size numbers just to keep our numbers small. So you're going to say, look, what I'm going to do is I'm going to use one of the bits to store the sign, leaving me only 3 bits to store the magnitude. So that means the largest value that you can store in 3 bits is 111, which is a 7. Okay. So with 4 bits, I can only store the numbers between -7 and +7. Somewhat limiting, but I can do it, right? So if we want to look at that, so let's look at, I'll just create another slide here. We'll call this sign and magnitude. Magnitude, I think it's that. All right, so our smallest number is -7, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6. And actually, let me just do this will be better to show what's going on here anyways. Copy this. So now we'll just take the negative signs off of these. All right, so let's deal with the stuff over here on the left first. So we're going to decide that a 0 in the far left bit is going to be a positive number. So that means a 7 will be 0, 1, 1, 1. A 6 would be 0, 1, 1, 0. 0, 1, 0, 1. 0, 1, 0, 0. 0, 0, 1, 1. 0, 0, 1, 0. 0, 0, 0, 1. And then what's 0? 0, 0, 0, 0. Okay, so that is our positive numbers. Negative equivalents, this will be 1, 1, 1, 1. This will be 1, 1, 1, 0. This will be 1, 0, 1, 1, 1, 0, 1. This will be 1, 1, 0, 0. This will be 1, 0, 1, 1. This will be 1, 0, 1, 0. This will be 1, 0, 0, 1. And this will be 1, 0, 0, 0. All right, so that's sign and magnitude. What's the problem with this? A couple problems.
First off, you have two ways to represent 0.
Yeah, I got two zeros. I got a negative 0 and a positive 0. That seems wasteful, right? All right, so so that must mean I've lost the ability to represent some other number at the cost of having to represent 0 twice. Okay? It also then becomes somewhat limiting based on the number of bits, because we're guaranteeing we're not using the far left bit for any data storage. We're using the far left bit strictly to represent sign. That make sense? Okay. So we have this thing called the 2's complement. So if we have the number 3, for example, we would store the number 3 as 0, 1, 1. Oh, that's not 3. 0, 1, 1. All right, so that's the number 3. That's positive 3, correct? If we want to store negative 3, we're going to store it in its 2's complement form. So negative 3 is going to, what we're going to do is we're going to flip all the bits. So this will be 1, 1, 0, 0. That's called the 1's complement right now. And you can use that for representing negative numbers if you want. But then you still are stuck with the 2 zeros problem. 2 ways of representing 0 problem. Okay, so if we actually look at this as the 1's complement, just to show you, let me steal this slide. Just we're complete here. So 1's complement. All these numbers will be the same. And I'm actually going to, I'll just write it again. Okay, so then this guy will be 1, 0, 0, 0. Then, actually that's correct there for the 1's complement. This guy would be 1, 0, 0, 1. This guy would be 1, 1, 0, 1. This guy would be 1, 0, 1, 1. This guy would be 1, 1, 0, 0. This guy would be 1, 1, 0, 1. This guy would be 1, 1, 1, 0. And then this guy would be 1, 1, 1, 1. All right? So there's another form of storing negative numbers.
-5 is
Oh, did I mess up -5? 1, oh, 0. 1, 0, 1, 0. Is that my only mess up?
yeah.
Okay. All right, so one's complement, where we just flip the bits, is pretty simple, right? No big deal. But we still have the same issue of two ways of representing 0, which means we've also then taken away we've taken away the ability to represent some other number. Okay, so this doesn't fully solve the problem. This does solve the problem. We're just not being efficient with our memory. And then we're also adding this additional thing of, really having to deal with 0 two different ways. Because a lot of times you'll see a lot of times when we're trying to do a conditional jump, we're trying to find out if some value is 0. Well, now that means is some value equal to this, or is it equal to this other thing? Because we have two different zeros. Does that make sense? All right, so that's 1's complement. Now, 2's complement, I'll steal that here in a second. Actually, let me just delete this one. I'll steal this one. We'll paste it. All right, so 2's complement is almost like the 1's complement, with one exception. That exception is that we add 1 to the flipped value. All right, so a -7 is the 1's complement of 7 plus 1. So we added 1 to that number. So that was 1, 0, 0, 0 plus 0, 0, 0, 1. That came out to 1 plus 0 is 1. All the other things just fall through. So this is 1, 0, 0, 1. Make sense?
But your computer's not going to read it as that.
You have to know it's stored in 2's complement.
Okay.
Yeah, because, and this is where, this kind of comes back to what we were talking about earlier. When we think about computer organization, a lot of what we're doing is we're deciding how do we represent data. And computers can choose to represent negative numbers in a way that might not necessarily be what we're used to, because we just throw a little negative sign in front of it. We just say, we're good. -7 right there. Okay? But computers need to decide they're going to represent those values differently, right? Okay? And that's okay. As long as if we're coding this thing and we're working with those values, we understand that that guy is encoded. You can almost think of it as being encrypted, right? He's encrypted using the 2's complement encryption algorithm. So I know that if I want to get the real value out of that guy, I gotta unpack it a little bit. I gotta do some magic to it. I can't just glance at it. Just say, oh, that's a -7 because it's got the little line next to it. All right, that makes sense? So we happen to know these are going to be stored in 2's complement if that's the way we've decided to do this. All right, so this guy, 1, 0, 0, 1, we're going to add 1 to that because these guys are already in 1's complement form, right? Because I copied it from the previous slide. So we're going to add 1 to that guy. So this is going to be 0. This is going to be 1. We're going to add 1 to this guy. We're going to add 1 to this guy, so it's going to be 0, then another 0, then a 1. We'll add 1 to this guy. We'll add 1 to this guy, so that'll be 1, 0. We'll add 1 to this guy. Okay, now, this guy is going to, we add 1 to 1, 1, 1, 1. This is going to be 0, 0, 0, 0, but stored in 2's complement form. So this guy is going to be -8. Now, we do have an issue here. I have room to store one extra value here, right? So I've decided, look, I don't need to store 0 twice. We already know that was a problem. But we look at all these negative numbers here. Every single one of them starts with a 1. Except this one. So this guy's actually going to be an 8 is 0, 0, 0, 0. And then we'll remove it from here. So we got an extra value on the positive side. And where have we seen this before? If we look at a byte, okay, if we're looking at signed bytes here, I'm going to put this on a different screen. So if I look at signed numbers, in our modern programming languages or something like that, so if we think about Java, for example, Java has something in it called a byte. A byte is 8 bits, and it's an 8-bit signed integer, right? Okay, what's the range of values that will fit in an 8-bit signed integer? It's -127 to +128. We got an extra value on the positive side because under the hood they're stored in 2's complement form. That makes sense? Because we didn't represent 0 twice. So if we'll just add an extra guy in here. If we have something called a nibble, which is what we've been working with, right? So that's a 4-bit signed integer. The smallest value is -7 to +8.
It makes sense, but like when the computer reads the number, it could read the same string, and it could be a negative number or a...
You're right. So your question is, okay, we're cool with now you have a way of storing those guys in positive and negative. As long as you know the secret, you can kind of figure it out. But how the heck does the computer decode it? That's your question, right? All right. So first of all, let's observe this. These are the 2's complement numbers for nibbles, right? We kept it with 4 bits. That way it was palatable for us. Nice small set. Every single one of the values here on the left have a 1 in front of it. If it starts with a 1, that tells us it's a negative number. If it starts with a 0, that tells me it's a positive number. Okay, and actually, I need to do... No, it won't be -8. Is it -8? -128 to +127? Then how do I represent the 8? So an 8 in this. An 8 would be a 1s, 2s, 4s. That's a 1, 0, 0, 1. That's an 8. So then I add 1. I flip all the bits. That's 0, 1, 1, 0. And then I add 1 to it. So that's that.
But that's 7. It's 1, 0, 0. Yeah.
1,
0, 0, 0.
Well, yeah. So for an 8, that's the binary number for an 8.
Right, because like imagine 7, you're taking away a 1.
Yeah. Right? So okay. So all I want to do is I want to flip those bits. So from an 8 to we got rid of this guy over on this side.
to 0, 1, 1, 1, and then when we add, it becomes 1 to 0.
All right, so we start with all zeros. Then you flip the bits. So that's 1, 1, 1, 1. You add 1 to it, and you're left with 1, 0, 0, 0. Right? Because what you got to do is you have to what we're removing here is we're removing a secondary representation for 0.
Yeah.
So then what we'll say here is we'll say a normal representation for 8 is 1, 0, 0, 0.
Yeah.
Now we need to encode it in 2's complement. So we flip all the bits. So that becomes 0, 1, 1, 1. Then we add 1 to that, which will be 1, 0, 0, 0. Okay, so that's the encoding. So this guy goes from -8 to +7. This goes from -128 to +127. So we picked up the extra value on the negative side. That makes sense now.
Is that what they do it as?
This is how they do it. Yeah, I just have my 2's complement wrong for the -8. This -8 isn't some special case. We did this the exact same way as all the other ones. Because I copied it, I didn't stumble across it the right way. So we started off with the positive number 8, which is 1, 0, 0, 0. Okay, that's the positive number 8. Then we flipped all the bits to get it into 1's complement. So that's 0, 1, 1, 1.
Right.
Then we add 1 to it to get it into 2's complement, which will be a whole bunch of carries. So we'll end up with 1, 0, 0, 0. Does that make sense?
Yep.
So the idea here would be is that 1, 0, 0, 0 is the same value for 8 as well as +8. We can't have it represent both. So that's why we gained the value on the negative side, and we don't have the ability to store an 8 on the positive side because we kept the ability to store the 0. We decided the 0 becomes part of the positive club, and we'll pick up the -8 on the negative side. But we didn't treat this as any sort of special case. It's still the 2's complement stuff. Okay? All right, so now, if we assume a value is in 2's complements, when we deal with signed numbers, that looks like this. Let's assume I have the number 1,000 based on this. So I have 1,000 in 2's complement. If I want to get that number, if I want to know what that number is, if I know that that number is stored in 2's complement, that has to be given information. I have to know that this number is encoded using 2's complement. Therefore, when I look at it right off the bat, I'm going to say this is a negative number. I know it's a negative number because it starts with a 1. If we go back to this chart here, all my negative numbers start with a 1. All my positive numbers start with a 0. Make sense?
Yeah, I thought you were actually putting those numbers 1,000.
Oh, yeah, well, just the binary, yeah.
Yeah.
Okay? So this is in 2's complement. So I know this guy is negative. So I'm going to go ahead, I'm going to perform 2's complement on this guy. So I'm going to flip it. So it's going to be a 0, 1, 1, 1. So that's the 1's complement. Then I'm going to add 1 to that. So we'll say plus 0, 0, 0, 1, which is going to give me 1, 0, 0, 0. That's the number 8. Well, here, let's do the arrow thing again. So that's the number 8. And because it originally started with a 1, this is a -8. All right, so understand that once I use 2's complement to convert it back, the value I'm looking for is just the magnitude of it. I already know whatever magnitude I convert will be a negative number because the original started with a 1. So now I use 2's complement to generate magnitude, and then I just throw a negative sign on the front of it because I know it must be a 1. It must be negative. Similarly, if we take 0, 100 for 4, let's say, I'll steal this guy. So 0, 100 in 2's complement. Because it starts with a 0, I know that will be a positive number. Okay, so I'll get the 1's complement first. That's going to be 1, 0, 1, 1. I'll add to that 0, 0, 0, 1. That's going to give me a 1 plus a 1 is going to be a 0. Carry a 1. A 0 plus a 1 plus a 1 is going to be a 0. Carry the 1. A 1 plus a 0 plus a 0 is going to be a 1. No carry. A 0 plus a 1 is, hold on, I screwed that up. Let me put them on top of each other. It'll make my life easier. All right, so 1 plus 1 is 0 with a carry. So I'll throw my carries up here. One plus 0 is a 0 with a carry. 1 plus 0 is a 1 with no carry. 1 plus 0 is a 1. It should not.
Why do you have to do the complement?
You still have to take it out of 2's complement to get the value out of it, but actually, no, you don't. You know you don't. This is a waste of time. So 0, 100, because it's a positive number, that means it's not encoded. So it is in 2's complement, it's already stored as a positive number. So to decode a positive number in 2's complement, we just use that positive number, which is a 4. This is a positive 4. All right, so we know that these values are stored in 2's complement. If it starts with a 1, we have to decode it. If it starts with a 0, we don't. Okay, but you still have to know that it was stored in the register in 2's complement form. So if you're storing in a register a signed value, positive or negative value, modern computing would store that as 2's complement. All right, so if you know you're storing it as a signed value, then when you pull it out, you would have to convert it if it started with a 1, the far left bit, most significant bit. If that was a 1, you know it's a negative number. That makes sense? Okay, so that's representing negative numbers.
That was always in nibbles, or are you going to have it look?
No, I mean, it would be in anything.
Okay.
Yeah, definitely not always in nibbles.
Okay.
Yeah, so I mean, if we, that would actually be an interesting thing to write anyways, because I want to do for our homework assignment some addition stuff. So let me actually give you a starting point for some of that anyways now. That'll take us up to kind of our next break anyways. So let me come in here. Let's just gut most of this so I can start from scratch. All right, so let's say that we were going to read in some value, some, maybe actually what would be interesting to do here is to go ahead and do the conversions like we did before in C, so that we could put in a decimal value, have it convert it to the binary value using the correct number of bits. So if we say we want to represent this as 16 bits, for example, let's just do a quick converter with this. So because this guy didn't make me prototype, I'm going to take advantage of that for the moment. So I'm going to go ahead, I'm going to read something in. So let's read something in from the user. So we use scanf to do that. So I'm going to say, let me get we're going to create an int called value. And then I'm going to go ahead and say printf, please enter a number. Then we'll do scanf, and we're going to be reading in a decimal value, and we're going to read that into value. And then we'll go ahead and print out %d\n and prove we read it in. I'll just spit it back.
Address. This kind of the address.
Oh, I have to give it the address of the value. So I'm going to read into the address of, actually, this is pretty similar to what we were just doing. So this is, I am loading into this address line. I'm storing into this address whatever was read in by scanf. So I'm reading in a decimal by scanf, storing it into the address associated with value. Then I'll go ahead and print out value proving we read it in. So let's run this real quick. Please enter a number. I'll say 34. Press enter. It spit the 34 out. So now I have a 34. All right. So now let's convert this guy to binary. But I'm going to read in, well, let's get the binary thing first. So I'm going to go ahead and write a function here. And this guy is going to return a char pointer, because it's going to generate the binary version of this guy. Okay. And actually, life will be easier if I actually do read in a second value here. So I'm going to say, please enter a number. I'm going to read in that number. Then I'm going to say, how many bits? And I'll read in bits. You could actually read them both in with a single scanf, but I'll just do it separate ones. All right, so I have the number of bits and the value. So I might say I want to represent 34 as a 32-bit number, for example. So what I would want my converter to do is I would want it to generate a binary number, the binary equivalent of that, and then pad it with zeros, okay? With enough zeros to have it balance out. All right, so we're going to go ahead and we're going to have this guy return a char pointer, and we're going to call this guy decimal to binary. We don't need to do it for any base. We're just doing binary stuff here, so we'll write it a little bit easier. And this guy is going to take in a int value and an int bits. Okay? And what we're going to do here is we're going to divide this value by 2 over and over and over again, building into a string. So I'm going to go ahead and create a string capable of holding this number of bits. Okay? So what I can do is I can divide that string by that number of bits by 8, and that'll give me bytes. So I can ask for the correct amount of memory. So I'll say char pointer answer is equal to malloc, and I'm going to say I want bits divided by 8. For the sake of argument here, we can just assume they're giving us a number that is a some multiplier of 8. Okay, some multiplier of 8. And you'll notice that in computer architecture, they are all multipliers of 8. You have an 8-bit register, or a 16-bit register, or a 32-bit register, so on and so forth. All right, so we'll say bits divided by 8 times size of char. We do need that, right? All right. So I'm going to ask for enough bytes. Actually, I can just... if I'm asking this for bits anyways, I think I can actually just say malloc and bits. Yeah, I can just, rather than convert it into bytes, then convert it into size of char. If I know how many bits, I can just say, give me that many bits. It'll mean the same thing anyways. If I convert it to bytes, then multiply it by size of char, that'll give me bits. But I might as well just keep it in bits, since that's what I asked the user for, is some number of bits. So this is going to get me some memory and associate it with this thing answer. Now I want to build my solution at the end of answer because I want answer to be filled up with zeros leading up to it. All right, so we're going to have to keep track of where we are in answer, and we're going to be building our, as we divide by 2, remember we actually read it from bottom up. So the very last value is the very first value we deal with, so we're going to have to build this thing in reverse. All right, so I'm going to go ahead and give myself a int pause. I'm going to start this guy off at bits minus 1. That's the last legal position in my string or in my char array. Okay, so the very first remainder I'm going to put there, and then I'm going to decrement pause as I go towards the beginning. All right, so now the very first thing I'm going to do, even though because I've asked for this memory, it's actually probably filled it with zeros, but I'm going to go ahead and put a bunch of zeros into that guy. There's actually a built-in function for doing that, but I'll just write a quick for loop. So I'll say int I for I is equal to 0, I is less than bits, I plus plus, the value at AR plus I is equal to a 0. So I'll go ahead and just fill my array up with a bunch of zeros. Okay, and actually this guy's expecting chars, so that would actually put whatever the Unicode value of, well, the ASCII value of a 0 is. So I'm actually going to fill it with the char 0.
No.
Yeah.
But you are putting character zeros. You want to put character zeros?
Yeah, because this guy's a char pointer.
Yeah, I understood what you're saying.
Yeah.
You want to put.
If you want to represent it as a string. If you want to represent it as an array of integers, you can, but this will allow me to print it out more conveniently if I have it as a string. Would you rather store it as an array of integers or array of bytes? I mean, yeah, I could always convert it back afterwards. I guess if we're going to do math with it.
You want to do memset? That is what I'm asking. You want to do memset?
Well, memset will just allow me to fill up the memory with a bunch of zeros. This will just manually do it. This will fill it up anyways. So now we got to decide, since we are doing just binary. So before we did decimal to base. So we had to decide what we had to store things like, you know, 7s and 8s and A's and B's and C's. Since we're just doing binary here, we seem to be going in the direction where we're going to actually be storing this as, we're going to do math with it. Maybe we do want to store it as either a byte array or an integer array. So because we don't care about memory today, we probably would say, let's say this is an integer array answer of size bits. And then when we store a value in here, we'll store the int 0 in there to pad it. All right, and he mentioned there's something called memset, which allows you to like kind of quickly do this for loop and fill everything in a block of memory up with a value. Okay, so now the whole thing is 0 to begin with. It probably would have been 0 anyways. Probably the default value would have been 0, but never trust the default value. All right, so now we're going to go through and we're going to do our divide thing for our value over and over and over again, and we're going to place the remainder at position pause in memory and then subtract 1 from pause. So we're going to be building this guy in reverse. All right, so we're going to say while value is greater than 0. So as long as value is still a thing, okay, there's still something in there. We're going to go ahead and we're going to say the value that lives at, and this guy is not called AR, it's called answer. My array was called answer, not AR. So I had to change it here. All right, so I'm going to store at position answer plus pause. The value that's going to go in there is going to be value mod 2. Okay? Then I'm going to say pause minus minus, and you could have done that in here if you wanted to, but that's very bad programming practice. do it on a separate line. So we'll say pause minus minus. And then, if you missed what I just said, we could have done that. And that would have been allowed. But that is very confusing code to read. Technically, since the minus minus came after the pause, we would get the current value of pause first and then decrement it. I would call it always bad programming practice to do something like that. I'm going to get the value of pause, and then on a line all by itself, I'll say pause minus minus. Make it one smaller. Okay? Then I need to whittle down value, so I'm going to say value is equal to value divided by 2 to make it smaller. Or you could divide equal if you wanted to use that guy. Okay? So this guy's going to go through until we finally whittle it down. It's going to be filling in my array. The only time we'd run into problems here if I gave it a value that was too big to fit in the number of bits. So just don't do that, because we'll have a carry in this case. All right, so now answer should hold. I'm going to change this guy to return a int pointer. Answer should hold my integer array filled with my values. Okay, so I'll go ahead and return answer here. All right, then let's go ahead and write a quick function that will print out the contents of an integer array just so we can visually see it. So we'll say void print array. This guy will take an integer array as a parameter and an int size. Say int I is equal to 0. Well, just int I, and then we'll do it in the for loop. For I is equal to 0, I is less than size, I plus plus. What are we going to do in here? We're going to go ahead and we're going to say a print f %d, and we don't need to put any spaces. And then we'll do the value that lives at AR plus I. Then after that, I'll do a \n. So print array, taking an integer array, taking how many buckets are in that array, go through, display the value in each of those buckets. This should be a whole bunch of zeros and ones, padded with a bunch of zeros at the very beginning. So that should show me my correct answer. Decimal to binary, we'll do the conversion. So now we've read in my two numbers. Let's go ahead and say int pointer answer is equal to decimal to binary, passing it my value, passing it my bits. And then we'll go ahead and say print array answer and bits. All right, so that should take me to the, that should print out the bunch of the zeros and ones equivalent of what I just had. All right, so let's start off with a simple number so we can test it. So I'll go ahead and run this guy. Oh, see, interesting. It's now I'm getting the implicit declaration of the stuff. Well, but it didn't. We didn't have to prototype it in here before.
Yeah, we did.
Not in this one. Did we still have to? I thought we saw earlier we didn't have to prototype. Yeah, I thought we didn't have to prototype it earlier. Yeah, interesting. Maybe it's only up to a point. Oh, I'll just leave the... All right, so please enter your number. So let's just do the number 4 as 32 bits. So there's my number. This is the 1's place, the 2's place, the 4's place. So there's my 32-bit version of the number 4. Make reasonable sense. All right, we try to run this again. Let's do a scarier number. Let's do 34 is my number. I want to do this in 32 bits. That's the number 34. So looking relatively solid. Okay, so now let's say that we want to trying to think on time. Well, let's at least talk it through, then we'll take a little break, and then we'll do our last hour. So let's say now we're going to read in a value, and we want to allow them to give us positive and negative values. So now what we're going to do is we're going to also have a function that converts a binary integer array into its 2's complement equivalent. Okay? So we're going to have, we'll probably have it create a brand new array. That way we have the original as well as its 2's complement so we can compare them. So this guy will return an integer pointer, and we'll say binary to 2's comp, something like that. Good enough. All right, and this guy will take an integer pointer as a parameter and also a number of bits for its size. All right, and this guy's job, now remember, whether we're dealing with positive numbers or negative numbers, we need to make a decision as to how we're going to encode it in 2's complement. We go back to our thing here, and we look at 2's complement. All of our positive numbers are stored as is, right? But we've said these are stored in 2's complement, which means what? If I have a nibble, 4 bits here, this far left bit is being used for the sign. Okay, so the point is that the size values that I can store, let's say that I try to store a, let's see, 1's place, 2's place, 4's place, 8's place. So let's say I tried to store the value 12 in a nibble. A nibble can hold the value 12 if I'm holding it in unsigned format, right? Because 1, 1, 1, 1 is 12, 13, 14, 15. Yeah, that's the size of a hex value, right? So if I don't want to store negative numbers, then I get to use all 4 of the bits to store my magnitude, store my value. The second I say I'm storing a signed number, I am immediately giving up one of my bits. That make sense? So if somebody says, I want to store the number 12 I want to store the signed number 12 in a 4-bit value, it can't be done, right? Because the signed number 12 won't fit in a 4-bit value. I need a 5-bit value in order to store that. Does that make sense? So the second I make a decision that whatever I'm reading in is capable of holding positive and negative values, I'm saying it's a signed value now. It's at that exact moment that I now have to say, I'm giving up one of my bits for the sign, so I've reduced my magnitude. But I know that if I'm using 2's complement, that at the very least, I'm going to fully use my magnitude. I'm not doubling up on zeros. I'm going to get an extra negative value out of this to use the whole magnitude. That makes sense? So we're going to assume that this thing, anything we read in here is going to be a signed number. That way we can do our 2's complement thing. And we can also assume that they're going to give us enough bit space to write our, to write our number. Okay? So the first thing we'll do is we're going to convert the number into binary, but we need to make sure that we give them the right number. Because if they give us a number less than 0, I need to store that that guy is going to be a negative value. And then I also need to convert the positive value version of him in order to then encode it into 2's complement. Okay, what I mean by that is if we come down here, if I want to, in my program, let's call this converter. If I say I want to store the value negative 7. The first thing that we do is we get the binary version of 7. Then we encode it in 2's complement form to store it as a negative number. That make sense? Conversely, I'll indent these guys underneath here. If I want the number 7, then I'll get the binary version of 7, and I'm done. I won't encode it. But the far left bit would be a 0. So you need to make sure you have enough bit space to hold a 7 plus 1. 1 bit more than the bit space it takes to hold a 7. That make sense? All right, let's take about 10 minutes. Come back, we'll do our last hour, and we'll go from there.